fine. This is nice because it doesn't expand any uncompressible data, assuming that you have one word that isn't used, a code word. But it reduces compression gains because every run has to be tagged specifically with that escape symbol. So it's both of those don't really make running the coding a scheme that's practical for real-world applications when you want real compression. And I mentioned those, as I already said before, mainly because extensions of these types of encoding, of these ideas, will become important later on. Another very, very well-known scheme in data compression, I assume most of you have at least heard of that as well, is delta coding, which is not an actual compression algorithm, but is a transform. So it doesn't try to make data actively smaller. It just changes the data in a reversible way, in the hopes that that you can compress it better afterwards. And what you do, assuming you have numerical data, like for example sound samples here, and you don't code the symbols themselves, but the differences between adjacent symbols. So the first symbol here would be a 1, because there's nothing in front of that. We just copy it over. Then we have 2 ones here, which don't get, there's no change from the previous symbol, so those get zeros. Then you have a small increasing sequence here, which just maps to 1, 1, 1, 1, and a jump here, which is, -3. And as you see, what's this noise? Okay, it's gone. As you see, this had basically no runs or repetitions in it, but this is already a lot, easier to compress because they are bigger runs. And it's good for that type of data, which is smooth data that varies slowly. So values don't change it abruptly, don't jump around all the time. For example, sound samples again. Those usually vary only by a small amount each sample point. So you get an improvement there because the differences are smaller than the actual sample values, and they tend to cluster around 0. And we'll soon see how we can take advantage of the latter, how that can make it more interesting for other compression schemes. And again, it's very simple and fast, and not much use for, say, textual data or binaries. So, quantization, which in this context strictly means using less bits to represent your values, for example, numbers. And it's the main lossy step in all kinds of lossy compression algorithms, say, for example, JPEG again. There are 2 main variants. One is scalar quantization, so-called scalar quantization, which is just, using less bits for each individual number. None of those values are grouped together, or you don't exploit similarity between those values, but you just code each number on its own. There's uniform quantization, which means that, the differences between samples are always the same. And, for example, when you have sampled sound again, you have 8-bit versus 16-bit, so the 8-bit is basically a quantized version of 16-bit sampled sound, or high color images with 15 bits versus true color images with 24 bits and the like. So it's always basically just cutting off bits. And that's how it looks. It's very simple, and it usually also produces very noticeable errors. And then there's non-uniform quantization, where you try not to make everything get the same step sizes, but try to make ranges that are important to you. Give them more range, so you can have a finer resolution there. For example, in floating point values, you give the values more precision near 0, because when you have a value on the magnitude of, say, 1 million, a difference of 0.1 isn't really that important. It doesn't change that much. But when your values are very small, like say 0.001, a difference of 0.1 is huge. And what floating point values do is that they give more precision to smaller values, and they divide this non-uniformly. And there are other examples you probably haven't heard of yet, because it's not that popular, actually. And then there's so-called vector quantization, which tries to code several values at once, which tries to group them. It uses a so-called codebook. So it's basically a table that tells you what a certain value means. You have a table of a few entries, and those just lists what values it gets mapped to. and it needs to be stored, which is typically quite small. An example would be, again, palletized images. You have this table of 256 colors you use, which are actually 3 values, one for red, one for green, and one for blue. And you use those 256 colors out of the whole RGB color space, and yeah, you compress this data from 24 to 8 bits. So it's it's a factor of 3 to 1, and decoding is basically a table lookup. And some older video codecs, like for example Intel Indio codecs, do a similar thing with groups of pixels. So they have, say, 4x4 pixel blocks, and they try to assign codes to those and just use a few of them. So everything gets small. And in an intro context, scalar quantization is usually fine. You don't need to get fancy. You don't want to get fancy because it makes everything more complicated. You get hard to find bugs. You get data that looks very random to any packer that runs after it. So you try to keep your code simple, and you want to keep yourself happy. You don't want any complications except coding the intro itself. And one such example for a very, very low cost quantization that really saves a lot of space is just throwing away the least significant byte of 32-bit float numbers. This reduces the mantissa size from 23 to 15 bits. If you don't know about floating point numbers, there's basically 2 components to them. One is the so-called exponent, which tells you what value range this number is in. I already mentioned you have very small numbers and very big numbers, and this exponent tells you what range this is approximately in. And this mantissa is the value which tells you where in that range the value is. And just reducing that mantissa size means, you have less resolution but the same value range. And it's usually fine for most data. Or you could also use so-called half floats, like you have in CG or HLSL, high-level shading language, which is a 16-bit floating point format, and it's also usable for lots of cases. And another example would be, say, for camera splines, where you usually have a lot of keyframes at a certain frame, or which is either in frames or milliseconds or whatever you use. And you have those time values stored and the key values where the camera is at that point. And what you can do is that you just store how long the whole spline is, and then just say, well, the start point of the spline maps to 0, the end point of the spline maps to 1, and you just code the time in between with a single 12 or 8-bit value. This means that the keyframes aren't positioned as exactly, but it usually, still is enough for, say, camera runs and so on. So this can save you a lot of space, especially when you use, say, 32-bit numbers before. And stuff like that is quantization. And if you do quantization, it's important that you round everything correctly, because this can cut quantization error to half, because if you always round into one direction, errors accumulate in that direction. For example, in Candytron, I was always rounding towards the left side, and so the face of the main character was very unsymmetric, because everything just got snapped left. And in the final version, I just fixed the rounding to something more sensible, which was say line of code, and it really made a big difference in appearance. So you need to take care of that if you do quantization. And the final one in this elementary techniques section is reordering, which is probably the simplest technique of them all I mention here, and it's the most important one for practical applications, because this is really where you can get the biggest improvement in pack rate with the least effort. For example, in Crunchy, my exe packer, I reorder the way instructions are stored, instruction opcodes are stored. And when you pack this with the Crunchy compression engine, for example, for Krieger without reordering, you get about 78 kilobytes. And after this reordering step, you're down to 65. So when rounding correctly, that's about a 12K